I think we can start now. Roger? Roger, can you, we will start our webinar. Can you start introduce something?
Yes, thanks, Hoshan, and welcome everyone to this WCRP, WRP joint webinar on monsoons. So today we're focusing on African monsoons. As an agenda, Akinsanola will give a brief introduction of the CLIVAR GEWEX Africa Monsoon Working Group, and then we'll have two talks, one after each other, and then we'll have 20 minutes question at the end. So just a housekeeping procedure. During the talks, if you have any questions, we encourage you to write your questions in the Q&A panel, and we'll get back to these questions during the Q&A session at the end of the talk. So Akinsanola, the floor is yours.
Thank you, Rondro. Good morning, afternoon, evening to everybody, wherever you're joining from. My name is Akintomide Akinsanola, and together with Rondro, we lead the Regional Working Group on African Monsoon as co-chairs. So currently we have about 22 members spread across the international community around the world. And our members are from within and outside of Africa. And unprecedentedly, we have 17 of the 22 members to be Africans. So our expertise largely is directly related to African monsoon climate, which involve disciplines on active research and modeling and observations. We have members who are from operational forecasting, and so what we have been doing over the years is, in a way, to narrow down to the challenges and activities across every aspect of Africa. So we have 3 active subgroups, which include the West studied West African monsoon subgroup. So we have subgroup on Central Africa, and the third one is on South and East Africa. So our overall goal is to identify the scientific gaps over Africa in the context of African monsoon. So, and some of the highlights, some of the activities we have been doing in the last two and a half years include presenting and also convening sessions at the international conferences and workshops. Example of this is our working group was actively involved in the WCRP workshop in Kigali in Rwanda. So we also convened a session at the just concluded AMS in Baltimore. I think the title of the session is on African climate change and variability. So, and as I said, one of the key aspects of what we do is to identify research gap in the context of African monsoon. So currently we have a review paper which is centered on the progress, challenges, and prospects of climate modeling of precipitation over Africa. So one of our subgroup, they are also looking at the added value of convection permitting simulation over the region. So, and in the last 2 or 3 years, we have facilitated active engagement and also collaboration among ourselves and also to scientists outside of the working group. So we are hoping to engage more to stakeholders over the region and also bring the research and also the gaps that we've identified to the operational guide in a way that the science can be put into use. So, and this year also we are planning to host a workshop in hopefully in collaboration to other international well-established agencies like WASCA or ICTP, where we can have hands-on training section. It's going to be hosted in Africa. We're still looking at the logistics, whether it's going to be partly virtual or in person. So this is what we have been doing, and we are open to outside collaboration. We are open to engaging at high level with stakeholders and with people who are interested. So again, thank you, and once again, I welcome you to this webinar. Thank you.
Thank you very much, Akinsanola. And as he mentioned, if any of his activities are of your interest, please get in touch. So we can start our webinar for today. We have two very interesting talks. The first one is by Michela Biasutti. Michela is a Lamont Research Professor at Columbia University. She was trained first as a physicist in Italy, and then after that she went to the University of Washington, Seattle, for a PhD in atmospheric science. In 2004, which is like 20 years ago, she moved to Lamont Doherty Earth Observatory to work there, and she is still there. So I just told her that maybe she's going to celebrate her 20th anniversary being at Lamont Doherty this year. Her research has focused on the dynamics that control the tropical rainfall, and especially on the West African monsoon. So we are really glad to have her here today, giving a talk on West African monsoon. But then her research interest has also led her to involvement in different activities like the WCRP Grand Challenge in Cloud Circulation and Climate Sensitivity. And I actually met Michela in one of his activities. Her interest also led her to the organization of a model intercomparison project, and the organization of different meetings and summer schools focused on tropical rain bands. And today she's going to give us a talk on climate change in the Sahel, the past and the future. And thanks a lot, Michela, for agreeing to give this talk today. And the floor is yours. You have 20 minutes for a presentation.
Thanks, Rondra. Okay, share, and here we go. Everything working all right?
Yes, perfect.
Okay, so thank you very much for having me. And I should start saying that, there's more to the West African monsoon than just the Sahel. Of course, there's a lot of interesting variability in the Guinea coast, but I've been focusing my career on the Sahel, and that's what we're talking about today. And so what am I gonna cover? The past, we're just going to look at the very long-term changes. I mean, not very long, but the decadal scale changes during the 20th century, and trying to figure out what was the ultimate cause, natural variability or anthropogenic forcing. What is the latest from CMIP6, and what's how does that fit with what we've known for a long time? And then we're going to look at the future and just how to deal with projection of Sahelian rainfall, and what are the parameters coming from CMIP6. And then I want to really close with some questions, right? The purpose of this working group is to figure out what the gaps in knowledge are, what the research should be. And so we really need to ask this question: how can we make progress? So let's get started with the easy. So this is a record of Sahel temperature. and in purple, and it's overimposed on the anomalies in global land temperature. And so it doesn't take a whole lot to understand what's going on here. The Sahel is doing what the globe is doing, and it's all anthropogenic. And so the relentless warming and a period between 1940 and maybe the mid 70s or 80, where the warming was not so pronounced. And in fact, maybe there was a cooling. But this is easy to attribute to anthropogenic forcing. When we think about the intense rainfall, that also is a record that fits very well with the narrative we have for the entire globe. This is a figure from a paper by Chris Taylor a few years back now, but it's a really nice analysis looking at storms from the beginning of the satellite era and showing that the contribution of extreme rainfall to the annual rain has been going up steadily, so that now they account for 25% of the total rainfall. What is more controversial to attribute is the record in seasonal rainfall or annual mean rainfall, which are basically the same thing. And so we see a record that is wetting in the first part of the 20th century, then a precipitous decline, and then somewhat of a recovery. But this decline period is not exactly timed with that pause in the warming that we saw at the beginning. So we're talking here about the late 1950s to the mid 1980s. That's where the rainfall was declining. So not quite the match. So how can we explain these multi-decadal swings? So the latest from CMIP-6 tells us that we can reproduce these decadal changes in atmospheric GCMs that are forced with the history of sea surface temperature and the history of the changes in atmospheric composition. So greenhouse gases, sulfate aerosols, and volcanic aerosols, and the rest. So here, the black line is the observed Sahel rainfall, and the green line is the multimodal average of these long AMIP simulations that are new to CMIP-6. CMIP-5 only had, from the late 70s. So now we can see the entire record, and we see these decadal swings. And if we take out the changes in atmospheric compositions, if we take that forcing out of the picture, we can figure out what the role of SST alone is. And that's the yellow line. And so you can see that, pretty much all of the variability here seems to be coming from the global ocean, where the radiative forcing giving a small contribution directly. But we can quantify that contribution by taking the difference between these two lines. And this is known in the literature either as the direct effect of radiative forcing, so what that happens because of how the atmosphere itself changes with the presence of greenhouse gases and aerosols, or because of the fast response of the land. And so what do we see here in this purple line? Well, we see that this direct response is small, right? So here the y-axis is changed here. So it's a smaller response than what we get with SST. But it does indicate the effect of volcanic eruptions. That seems to be reasonably solid response. And especially it indicates some extra wetting that is coming above the noise in recent decades, as the greenhouse gases have been going up and the aerosol has been going down, at least in the Atlantic. So I'm pointing this out because we're going to come back to this. But for now, what we want to know is, the first thing that is new to CMIP-6. It seems like the timing and the magnitude of Sahel rainfall anomalies are captured when SST is prescribed. And so this the connection with SST has been known for a long time. What 20 years of model development have given us is the fact that the magnitude of the variability is reasonably realized in the model. So the 2003 paper by Giannini et al., the first that really showed this very good correspondence between model and observation in Sahel rainfall, was hiding the fact, not hiding, it's in the text, but not in the figure, right? But it was the variability in Sahel rainfall was a fraction of, in the models that it was in observations. So now we actually get a very good match to the magnitude of the variability. Okay, so we get it if the SST is prescribed. What if we don't prescribe the SST? What if we use a coupled models and we just impose the atmospheric composition forcing and we let the model come up with its own SST? No good news there. So here is a figure taken from the chapter 10 of the IPCC report. And what we're trying to do here is, let me see if I can get the pointer. So what we're trying to match here is a decline in rainfall during 55-84 and a recovery between 85 and 2014. And all these other rows here are model simulations. So you see the extent of each simulation. So here we have the signal and the noise, right? And what's disturbing is that we don't get the full extent of the anomalies. The signal is roughly right. So we get more drying when it should be drying and more wetting when it should be wetting, but the magnitude is not there. Is this a problem with SST? Likely, right? And so how to look into that, what we've done is to come up with just one index of what the SST is doing. And this index is taken from Giannini et al. And it compares the temperature of the global tropics, which are the ones that set the stability of the atmosphere, how easy it is to convect. And it compares it with what's going on in the Atlantic. And the Atlantic here is a stand-in for basically the local circulation, the local input of moisture into the Sahel. Can you meet the ante set by the global tropics and convect? So we take this simple index and we look at what the couple models do with it, and they get that wrong. So what they do is they produce a slow decline and then this increase. That's both CMIP6 is in the dark blue and CMIP5 is in the lighter blue. And so we see this going towards negative values till the 70s and then coming up towards positive values. The observations are doing something somewhat similar, but they have this large swing that is not captured at all. And so by doing this wrong, they also get the Sahel wrong. They get this slow decline and then the recovery, but they don't get these swings. But I should point out one more thing, and that's the fact that the timing here of when the minimum is and when the recovery starts is somewhat different in CMIP5 and CMIP6. And so CMIP5 is, the magnitude is all off, but at least it's correlated to observation at 0.4. Now, 0.4 is not a huge value for correlations, but remember that the AMIP simulations were correlated at 0.6, so 0.4 is not bad. When you look at the CMIP6, the correlation is 0, just smack on 0. So somehow something went wrong between CMIP5 and CMIP6, and it's really not coming from this oceanic index because they're on top of each other for that. So what gives? Well, if we take out the linearly, by linear regression, we take out that index the variability in Sahel rainfall that is associated with NORCE. So we take this residual, and this is the residual for CMIP 5, and this is the residual from CMIP 6. And what I've superimposed on it is that estimate of the fast response that we got from the AMIP simulations. And so it seems like we're getting this extra wetting at the end of the record that further degrades the CMIP 6 simulations. Where does that come from? Well, and why it's not in CMIP 5? Well, CMIP 5 and CMIP 6 have different sensitivities. We know that the new ensemble is more sensitive, for example, to greenhouse gases. It turns out that CMIP 5 and CMIP 6 also don't have the same forcing. There's really nice work coming out of NCAR where they take the latest, the CMIP 6 generation NCAR model, and they run it with both the CMIP 5 and the CMIP 6 historical forcing, and their climate is pretty different. So there's something in the forcing, but also, of course, the models themselves have changed. Another possibility, or not mutually exclusive, but something else to note, is the fact, it's something that is coming out of work by He et al., Chen-Fei He et al. And what they show is that CMIP 6 models have a spurious trend. So if you compare the pattern of SST interhemispheric difference, you get this stronger interhemispheric gradient in CMIP 6 than you get in observation. And so it could be that this pattern of SST affects Sahel rainfall in a way that is additional to what we were able to capture with NORCE. My inclination is to think that what we see here is something that is due to the response to greenhouse gases, as is the direct response in Sahel rainfall. And so the two are, showing up together because they have the same forcing. They're confounded, but one is not the cause of the other. Okay. So, and I should point out that in this paper, He et al. Also think that, they do two things. They detrend the Atlantic and the Sahel, so the Atlantic SST and the Sahel rainfall, so that they want to take out this spurious gradient that they think is a spurious response to greenhouse gases. And then they rescale the response to bring up the variability, and they think that they need to do that to bring out the response to aerosol. And when you do those two things, you get a good match between models and observations. So models in blue, observation in red, both in the Atlantic signal and in the Sahel rainfall. Now, this is a lot of massaging the data when you're looking at multi-decadal signals. So, do as you wish with it, but this is a nice new paper, and I figure this is the latest. I needed to show you what the latest is. Okay, so what will happen? Well, first of all, again, CMIP 6 is not telling us something that we didn't know from before. And in particular, it tells us that the rainfall projections are complex. So just as it was in CMIP 3 and CMIP 5, we see this difference between the Western Sahel and the Central Sahel. In historical observations, these two have been changing together, but now East and West have different anomalies. And I should say, this is, I saw that Paul Arthur is in the audience, and this is really his work. So I should shout out to him. So that's the first thing. These anomalies are complex. The other thing is that they continue to be very uncertain. So if you take the anomaly in the Western Sahel, they go from negative to some outlier model that is very wet. And in the Central Sahel, we go from not much happening to quite wet. And unsurprisingly, we can trace back these different, the spreading of the simulations to the fact that we have different SST anomalies in the model. So what Paul Arthur has done is to basically find what the N members of this broad distribution of projections are. And so you come up with two patterns of SST, one in which the Atlantic is warmer than the global mean. So if you take the blues here, obviously we have warming everywhere in the future. But if you take that global mean out, the blue indicates places that warm less, and the reds indicate places that warm more. And so models in which the Atlantic warms more than the global mean give you a wet Sahel. Models in which the Atlantic warms less than the global mean give you a dry Sahel. And this is like the view from the composites, and this is the linear view. If you regress the uncertainty in the projection of Sahel to the with the SST pattern, so taking out the any global mean temperature, but you get this interhemispheric pattern again with the stronger. With a lot of the anomalies that drive the uncertainty coming from the Atlantic. And so, there's a problematic pattern that keeps happening, right? Where it's either not done quite right in the historical simulation, and it's also the one that drives the uncertainty in the future simulation, in the future projections. So what have we learned so far? That the Sahel rainfall is sensitive to the pattern of SST changes, that current AGCMs capture this sensitivity fairly accurately, but the coupled GCMs can't do it, right? They seem, if Changfei is right, they seem to overestimate the interhemispheric gradient that comes from greenhouse gases, and they underestimate the Atlantic SST changes that come from aerosols. And there's an uncertainty in how this same SST pattern will evolve, and that drives uncertainty in Sahel rainfall. So what do we do now? How do we make progress? And I think there's two issues here. How can we adapt to climate change in the real world, right? And what is the research we need to be doing? So for the adaptation, I really like this quote that I learned from Ted Shepard. This idea that, if we can learn to substitute evolution from what we know for evolution towards what we wish to know, a number of vexing problems may vanish in the process. And what we wish to know is what we need to do. And so we might not have to know exactly what the projections are to know what to do. And so we can, there's a lot going on that can focus on the adaptations to address heat, to address downpours. These are parts about the climate change that we know for sure are coming. And they will also help with the interannual variability of the mean rainfall. And so a lot can be done without even knowing exactly what the projections of seasonal rainfall are going to be. And as long as we, but we should keep an adaptive decision-making process. And at a certain point, when we find out what the Atlantic is doing, maybe we'll adjust. In terms of climate research, well, we need better climate simulations, and we need to figure out what was exactly the forcing in the 20th century. And we should figure out if we need to solve a signal-to-noise paradox in the model that seem to not respond sufficiently to aerosols in particular. But I have known insights on these things. I don't, I'm leaving it to the new generations. What we can work on, though, is observational constraints. What is the range of natural variability in the Sahel besides the 20th century? And also, if we want to know how it responds to the direct changes in atmospheric composition, we can look at maybe volcanic aerosols, but we need more data. And so to do that, one thing that we can do is to go to paleo data. And so right now, drought atlases in existence do not cover Africa, but we know how to do dendrochronology in the tropics. And so, and there's hope that we can do this for West Africa. These are trees from Senegal that show nice rings, and we have a proposal out to try to get funds to go core some more trees and figure out what was the rainfall variability in Africa. If you're a reviewer of the proposal, please give us money. And so I'm coming to my conclusions. What has happened? Well, the changes in the global oceans have caused these 20th century pluvials and droughts, and the 21st century recovery. Volcanoes add to this interannual variability. The attribution remains very tricky, right? We have expert judgment saying the models are wrong, but it's challenging when you don't know how come the models are wrong, and so they continue to, obviously some of them continue to be wrong in the future because they project both rainfall drying and increase. So some of them are wrong, but we can still focus on adaptations that are robust to the uncertainty in the mean rainfall change. And we have lots to do to understand how the models respond with this gradient in SST to the external forcing, and to collect data and build better record for past the Sahel rainfall. So thank you very much. We'll take questions at the end, I guess.
Yes, thanks very much, Michela. That's super interesting. I think we can move to the next talk. And again, if you have any questions, please jot them down in the Q&A panel, and we'll get back to that at the end of the second talk. So our second speaker is Samson Hagos. He's a senior scientist at the Pacific Northwest National Laboratory. Samson, he completed his bachelor degree in physics at the University of Asmara, Eritrea. And in 2008, he graduated with a PhD in atmospheric science from Cornell University. And then he was a postdoctoral research associate at the Rosenshall School of Marine and Atmospheric Sciences, University of Miami, before joining PNNL, where he is today. Samson's research interests are focused on understanding and modeling of precipitation processes over a wide range of spatial temporal scales. So that is from the life cycles of individual convective cells to tropical intraseasonal oscillations, atmospheric rivers, and interannual to multi-decadal variations of monsoon systems. Samson was a recipient of the 29 Clarence Leroy Messenger Award from the American Meteorological Society from his contribution to the field of tropical climate variability. And recently, he was nominated to be a new member of the CLIVAR GEWEX-Monsoon panel, and we are very happy to have him as a new member of the African Monsoon Working Group. So welcome, Samson. And thanks also for agreeing to give this talk on synchronization of the recent decline of East African long grains and Northwestern Asian warming. The decline of East African long grains have been a hot topic also in the community. So it's a very timely talk. And the floor is yours. You have also 20 minutes.
Thank you, Rondro. Thank you, everyone, for coming to this presentation. This work is done in collaboration with my colleagues at PNNL. It looks at the covariability of the recent East African long grains decline and warming over Northwestern Asia. To set the stage, the region that we refer to as East Africa is delineated by the red box here. As you can see, it covers a wide range of latitudes. Therefore, it looks at different seasonal cycles. If you look at further north, you see that North African monsoon kind of variability, where you have peak precipitation in June, July, August to September. As you go further south, you have that double peak at the ITCZ crosses the equator twice. And then further south, you have a single peak in northern winter. So we are covering a fairly large region here. So why do we care about this problem? It has been in the news recently, especially last year, the droughts over Kenya and Somalia and their impacts on food resources, water resources, and livelihoods of people. So this problem of extreme droughts is still with us, as was the case in the 1970s and 80s, as Michela pointed out. So the general understanding of this problem, the variability of East African precipitation, goes to mainly the variability over tropical oceans. The main idea being, if you have warming or cooling over the maritime continent, for example, in response to ENSO, you would have enhanced subsidence over West Africa, which suppresses convection. So a lot of this variability has been discussed in the context of variability of ENSO, IOD, or TO being weakening or strengthening the Walker circulation. So the problem we are discussing here is that decline in precipitation in between 1980 and 2014. You see that in many of these observations, as well as global analysis. We show here observation trends, 35 years of trends in GPCP, in CRU, in ERA5, and in our model simulations. ISRI-HM is a US Department of Energy global climate model forced with observed SST. You see that dry even stronger than what has been observed. So one thing we looked at here is the role of land surface feedbacks. So to understand the role of land surface feedbacks, what we did is we had this control simulation and ran it for 35 years. Then we took the first year, 1980, we have 12 months. So every month of that of the initial land simulation, we kept the initial land surface condition of that of 1980. So there is no interannual variability in the initialization of the land surface. If you do that, what you get is the green line on the left-hand side. So a lot of that trend is essentially eliminated when you reinitialize the land, when you keep the land in the 1980s condition globally by just restarting it by the 1980s months. So if you have January of 1987 in the init land simulation, we just replace it by the 1980s January and so on. So that means the land has a big role to play in this decline in long-term precipitation. So then you can say, well, which land? You know, we are talking about a global land surface reinitialization, and then you can take the interannual variability, take average precipitation over that red box that I showed, and then you can look at the difference between land surface temperature of that initialized land simulation and the control simulation. And if you take that average of precipitation over that red box and do correlation with every grid box on around the world of land surface temperature difference, you see that much of the warming over Northwestern Asia has something to do with the dry conditions over Eastern Africa. So the peak red condition, red that is showing negative correlation, between local precipitation and local land surface condition is expected, in the sense that if it rains, the land surface is cooler. But the remote is something that's interesting. So we can run idealized simulations where we say, okay, so how would African land surface precipitation over East Africa, that is, respond to a warming, to an initialized warming of just 0.5 degree Kelvin? That's an estimate of the change in warming over that 30-year period. And if you do that, what you find is indeed it leads to dry conditions over Eastern Africa, just by imposing that warm condition over Northwestern Asia. So that, of course, is what the model is saying. So then the question is, do we have any observational evidence for this? Before looking at the observational evidence for this, what the mechanism for this? So now we are talking about the model, so we can calculate, for example, the regional Hadley circulation averaging between 30 east and 50 east. That's the longitude where we are looking at relationship. And sure enough, you see the weakening of that regional Hadley set. So the warming would essentially weaken the convective activity, the updraft over Eastern Africa. So that kind of conceptually one can understand that the warming of the land over higher latitudes would interfere with the Hadley set. So we see that in the control initialized simulation difference, as well as that idealized simulation that I just described. So that's what the model says. Now, we can see if we see any similar correlation in observations. So now what we are comparing is March, April, May precipitation in that red box, and how it correlates with land surface temperature, corresponding land surface temperature around the world, very similar to what we did for the model. So on the left panel, you see correlation between GPCP precipitation, March, April, May, GPCP precipitation, and land surface temperature. And you see that correlation over much of Europe and Northwestern Asia. You also did the same thing with the CRU precipitation and land surface conditions. We still see significant correlation there. And University of Delaware precipitation and land surface temperature also shows that. And finally, we see that behavior in ERA 5 as well. So we see statistically significant correlation between average March, April, May precipitation over East Africa and the land surface temperature over Northwestern Asia and much of Europe. So how does that do that? We can look at the composites from ERA 5. So we can take the years where you have warm surface conditions over that green box that I show here, and when the years when the conditions are cooler, then you can composite other variables with respect to that. So if you do that, this is the difference in precipitation that you get, statistically significant correlation over much of Equatorial Africa, including Central Africa. You see that dry conditions associated with warm conditions over Northwestern Asia. So what's happening is basically, as you can see in the circulation patterns, the moisture, as you have the subsidence, the moisture, or in this case, column integrated precipitable water is diverted away from much of East Africa, according to ERA 5 analysis, as we have shown in the ISRSM simulations. Then we can also relate this to SST patterns. So if you do that same thing, composite warm conditions over Northwestern Asia and cool conditions over that same region and difference them as a composite, you see SST patterns that look like what's shown on the right-hand side. So what we see is essentially what resembles to what looks like a cool PDO, or rather more like also La Nina conditions that could potentially be affecting the land surface conditions over Northwestern Asia. There are evidence of such impacts of SST patterns on land surface conditions over that region. So what we are saying is not so much that the land surface conditions forced by themselves forced this drying over East Africa, but it the mechanism, the SST patterns, the cool phase of PDO could affect the warming over Northwestern Asia. Then that the resulting change in circulation could ultimately affect East African precipitation. So again, the point here is that the impact, we are not saying that's exclusively due to land surface conditions, but potentially through direct impacts of the SST, indirect impacts of the SST through modulation of the land surface conditions. So in summary, in contrast to previous work which focused on global SST and direct impact on global SST, now here we look at the impact of land surface feedbacks. And we find that the warming over Northwestern Asia introduces subsidence over Eastern Africa and could result in cooler or drier conditions over East Africa. So further idealized simulations show that in the absence of that feedback, as they have shown, the direct impact of SST by itself appears to be limited. So what we are pursuing this path right now is looking at the implications for East African climate paradox. For example, how do CMIP6 models represent this robust relationship that we observed, and can we differentiate the credibility of models based on the on how this relationship, or how strong this relationship is in those models, and hence their implications for trustworthiness of their projections. So that's all I have. I welcome questions and discussions.
Thank you. Thank you very much, Samson. That's very interesting. So now it's time for questions. If you have any questions, please type them in the Q&A panel, please. We actually have a couple of questions. I think mostly for Michela for now. Akinsanola, you want to go ahead and get the questions?
Yes. So thank you once again to the presenter. So one of the questions we have here is from Mohan. His question is, how does the spatial and temporal pattern of sea surface temperature in African monsoon region influence rainfall uncertainty?
Sorry, am I supposed to read it here? Because I don't see it. Can you repeat the question?
So the question is, how does the spatial and temporal pattern of sea surface temperature in the African monsoon region influence uncertainty, rainfall uncertainty?
So the pattern that is most important for the uncertainty of projection is really global. It's not really the SST in the, at least according to the models, right? It's really not the SST in the area nearby the monsoon. And so what we find is that it's this, so people might interpret it differently, but either in terms of this SST gradient between the north and the south, or more locally, like the role of the Atlantic. And depending on how you look at the same pattern and what you take out of it, what jumps at you, the mechanisms are somewhat different. So the interpretation for the interhemispheric pattern is that it would affect the entire rain band, the entire ITCZ, and with the idea that the whole ITCZ moves to the hemisphere that is anomalously warmer. If you think more in terms of the Atlantic, I think that to me, the explanation that makes the most sense is the fact that warm Atlantic temperature affect then the temperature of the land, of the Sahara, changes the local circulation around the heat flow, and that will change the progression of the monsoon. So those are the two paradigms I keep in mind. I'm not sure if it's answering the question.
So the next question by Mitra Hashis is, how good or bad is the interannal variability in the model versus observation for historical period? How good or bad is the interannal variability in the model versus observation for the historical period?
It's so if you impose the correct SST, it's not bad, right? So you get 0.6 correlations, and it's good throughout the record, even in the beginning. So in fact, I saw that there's a question later about the data sets used for the Sahel rainfall, and to some degree the fact that the correlation between observed Sahel rainfall and that simulated with an AMIP simulation is so good, it kind of also makes you think, oh, the observations are good enough even at the beginning of the century, because otherwise we wouldn't be getting these correspondence. So I think that it's obviously there's quite a bit of natural variability, internal atmospheric variability, but it's we see the right correspondence for the right reasons, the same connection between the SST pattern and rainfall is in model as it is in observation. So that's another good thing.
Okay, so this is from an anonymous attendee. So they said Dung and Sutton 2015 claimed that SST had led to the Sahel rainfall recovery from the 60s to the 2000s. So the question is there any merit in their result?
So the way I think of this is that when you're just looking at whether you get a trend, you have 1 degree of freedom. And so if the SST gives you a trend and that's what you're looking at, you can go like, yay, I got it from the SST, that's all I need. And if you impose just the greenhouse gases and you get a positive trend, you can go, yay, I only impose greenhouse gases and I get a trend. So what we see in the models is that you get that recovery either with one or more weakly with the other. So the greenhouse gas do give you a direct wetting without having to involve the SST. It's significant, it's not as strong, but it's there. You can get a whole lot of the signal without that. So
okay, so Lee is asking if the SEMIP model simulates Saharan dust, its radiative feedback, impact, land use changes, and dynamic vegetation. Do the coupled model intercomparison projects simulate Saharan dust, radiative feedback, impact, land use changes, and dynamic vegetation?
So the dust is there, but I believe it is not interactive. And so these land use changes also are there in some crude ways. There's the vegetation changes in characteristics, so leaf area index and things like that, but it doesn't go from tree to grass for most of these models. So those are things that are problematic, but I think that what we can put together from so the dust could definitely affect the sea surface temperature in the Atlantic. So that I can see being a very important feedback, right? But given that we see this strong connection with the SST, local vegetation processes might be secondary. And in the having said that, the couple model, the AMIP models, as I show, get most of the variability in, but they don't get the full extent of the variability. So maybe there's also some room there.
Thank you. So this question is for Samson. The question is, how applicable are your findings for operational forecast during the March to May season? The question is from Marceline.
Can you repeat the question? I'm trying to read it fast.
So how applicable are your findings for operational forecast during March to May season?
Yeah, that's something to look at. For example, now we are talking about, correlation without lag, right? Just take average precipitation March, April, May, in March, April, May land surface conditions. But if you really are into forecasting, the question is how much lead time can you get? Maybe we should look at, February. Does we get correlation with February temperatures over Northwest Asia, or something like that? Then that would give you one lead of a month, or January, 2 lead, 2 months lead, and so on. So that's something we can look at easily because we have the data set. So if it turns out that we have robust lagged correlation, then I think this could be of some value to sub-seasonal to seasonal prediction.
Yeah, thank you, Samson. So another question from Alan, I think to Michela. He said the general outcome of your presentation looks like a coupled model are not appropriate over the Sahel. So he is saying that similar results are also obtained when you have a coupled global ocean component with a limited atmosphere component in the context of regional climate model. He said this may suggest a complex or even nonlinear control of the SST over Sahel. Local forcing factor of the West African monsoon may also have stronger imprint than the mesoscale or the large scale driver associated with SST. So he's asking the opinion, what you think about this.
I'm not sure I'm understanding the idea here is that so we have a global ocean, right? And forced by a fixed atmosphere in most places, but interacting with the West African monsoon. I haven't thought about it. I'll have to take this offline. Can you send me an email and we can discuss it, because it's an interesting hypothesis.
Yeah, so Harlan, please contact Michela for a follow-up discussion. So Lester is asking question about observation used in the Sahel region. So how was it obtained? Are these in situ or remotely sensed?
So it's these are from station data, graded by people who know how to do these properly. But it's really not, I mean, you can take any different data set and you can merge it with the latest iMerge and everything, and you would get the same changes. And then I said before, so for, the comparison with the remotely sensitive in the recent period is good, even for the station data-based data sets. And also for the beginning of the record, I think, as I was saying before, the fact that AMIP simulations actually get those inter-annual variability kind of also gives credence to the fact that the record is good enough to get this variability, at least at this very large scale.
Okay, so a question by Saul. The question is, considering the differences between the semi-5 and the semi-6 in the mean Sahel precipitation do not derive from NARI? I don't know what that
Yeah,
means.
the North Atlantic Relative SST Index, that index that I defined.
Okay.
Yes, very good question. Where do they come from? So, as I said, I mean, the questions are still up in the air. One possibility is that the CIMIP-6 respond to these, they have a stronger response to the greenhouse effect. So we see it in the global mean sensitivity, but we also see in the interhemispheric gradient, as Chen-Fei He and et al. Have shown in this paper in 2023. And so it could come from that. That would be putting the blame on the direct effect of greenhouse gases. As I said, the NCAR people have shown that the difference in forcing between CIMIP-5 and CIMIP-6 is also substantial, and in that case, they're talking about the importance of differences in the aerosol. So the CO2 forcing hasn't really changed, although the sensitivity to the forcing has changed, but the aerosol forcing has changed between CIMIP-5 and CIMIP-6. So I would love to see this, swap in forcing, but we haven't done it yet.
Okay, thank you. So another question is, what about the role of the intertropical convergence zone and the Saharan heat low on West African monsoon rainfall?
Good question too. So as I said, I think of the ITCs, of these two things as complementary. They both yank the Sahel rainfall one way or another. With the ITCZ really making that shift being more zonal, right? And I'm thinking that the Sahara heat low might be getting more and more important as we see this difference between the East and the West appear. The only explanation I have for that is, the localized, changes that come, from the geostrophic flow around the low, right? And so I think if the models are correct, this is going to be more and more important. But yes, absolutely. And that might be the explanation for why the Atlantic has such a strong role.
Okay, so another question by Annalisa Churchy to both Samson and Michela is, what recommendation do you have for the global climate model development towards semi-7? Specifically, what land surface processing or feedback are the most urgent to consider at this stage of the monsoon and for Africa? At this stage for the monsoon and for Africa, yes.
So, Annalisa, nice to hear from you. Oh man, model development is above my pay grade. I got nothing for you. I know I would focus on this question of the signal to noise paradox, because I really don't understand it. How do we have models that correlate better with observations than with their own ensemble members, right? We seem to get the signal right in principle, but so low in amplitude. Why is that? And I know that people have talked about resolution, I've talked about, but I got nothing for you. Samson, take it.
Yeah, sure. I could try. I think for land surface, I hope it receives as much attention as as SST. Well deservedly we pay a lot of attention to SSTs, but important land surface feedbacks could be give us clues. For example, we know that there are models that just rain over wet areas, while observations clearly indicate by work of many like Chris Taylor and others that show that the precipitation patterns, especially new convective initiation, takes place over dry areas. So these metrics need to be really examined in models, and we need to make sure that the right kind of feedback, land surface feedback, is in these models, because who knows, this could have potential impacts on SSTs too. If the monsoon land surface feedbacks on monsoons are not well represented, then the surface winds over surrounding coastal areas are not well represented, then who knows what they do to SSTs. So I think correct representation of land surface feedback should receive attention.
Yeah, thank you, Samson. So this question is for Michela. How is the predictability for the Northwest Asian warming?
Are you sure it's for me? Because the Northwest Asian warming was in Samson's talk.
Yeah, so I was surprised too. I think this should go for Samson.
I guess it's or Samson, yeah.
Yeah, because I don't know the answer to that question.
Yeah. Samson, could you please answer this if you can?
Gone offline for a second. There's one more for me later
Yes,
about extreme rainfall.
So this is from Bello, and he said extreme rainfall is recovering faster than the mean rainfall according to some study in the Sahel. How is that captured in the CIMIP model, and what are the sources of uncertainty?
Okay, so abysmally would be the answer for how extreme rainfall is captured in models, in the sense that the way the extreme rainfall actually happens in the Sahel is mesoscale convective systems, and you don't get those at the resolution of CIMIP models. You only get those when you have, convective permitting resolution, so a few kilometers. So we do not get the right distribution of rainfall. This is known in the literature as the drizzle problem. You have a lot of small rain events and not the big rain events. Having said that, the models do show an increase in intensity in rainfall, but they show it because that's kind of the default mode when you increase the humidity. And so the precipitation distribution shifts to more intense rainfall. And so you can look at the fact that they do the trend correctly and be happy with it, but on the other hand, they don't have the mechanism that really gives us extreme rainfall. So the convective parameterizations are all based on some sort of convective equilibrium assumptions, and a mesoscale convective system is kind of by definition something that is not in equilibrium, right? That's something that organizes itself, makes its own environment so that it doesn't get rid of CAPE as fast as possible. So we're getting the right trend for the wrong reason. But there are models coming online. We're looking at them as we speak, and I think there's a lot to be done in that area.
Thank you. So I think the questions are now for Samson. So one of it is how is the predictability of the Northwest Asian warming?
Well, we have not looked at it yet. We haven't gotten that far yet, but that's something we want to kind of pursue going forward. We have some initiative looking at predictability of land surface conditions. So we intend to look at it as part of a more global land surface conditions predictability.
Okay, so another question for you, Samson, is you mentioned about the droughts during the 2021-2022 in East Africa. There's excess rain in October, November, December in 2023, and recent research have shown that the Indian Ocean Dipole and Henso combined phase control rainfall during October to December in the region to a large degree. So I said even prediction could be made one season in advance based on those phases in the June to July to September. So hence indicate about the major role of natural variability. So I'm not sure I see the question here.
Yeah, I read that too. Yes, I agree that a lot of the variability, as I put in the introduction, especially for the short rains, October, November, December rains seem to be directly linked to that Walker circulation, SST patterns in the tropics, and there has been some value of prediction gained from that. And for long rains, things are a little bit more complicated, as I showed there. So I think, again, we are not ruling out the role of SSTs, but once we understand, we frame the problem as not just SST directly impacting the East African region, but potentially affecting other regions, and other regions affecting East Africa, that could be a potentially fruitful path forward for prediction and predictability. That's kind of what we are proposing here.
So I think all the questions here has been adequately answered. Thank you, Samson, and thank you, Michela. So Rondro.
I think there is a question by Michela to Samson.
Yeah, I saw that too. Michela, can you clarify that? Are you talking about other regions of Africa, like West Africa?
Would you expect this? Well, I was just thinking in terms of like, so you see this connection between Northwest Asia and Africa, and I'm thinking are the land feedbacks going to be similar in given that the ecosystems are probably very different, etc.? Do you expect that is the same kind of, like, that the model development would have to be taking into account something different, or that if you fix it in one place, it's going to be fixed someplace else? How do you see that?
Well, we will have to look at it, I think, carefully, region by region, and sort of pay attention to the nature of land surface feedback these models produce. If the nature of the feedback is wrong altogether, there's really no point in kind of doing this analysis. I think the first thing is, where does it rain in comparison to existing soil moisture or land surface temperature? That would be a good place to start, and then go from there. I think there's a lot of work to be done in just that space. Where exactly does it rain given land surface conditions? Many models say it rains in that wet area, but clearly in observations, it's really the sensible heating associated with that gradient between wet and dry area, and it's really at the margins that you see a lot of strong impacts on precipitation.
But is that just for like the tropical convective systems, or would you expect something like that to also happen in the mid latitudes? That kind of.
I think in the mid latitude, it's really winter kind of. A lot of the precipitation would be winter anyway. The land surface feedback wouldn't be as as relevant as monsoonal environments. But for summer precipitation, there seems to be important role being played by land surface.
Thank you.
I actually have 2 questions for Samson, if I may. So
Sure.
one is in your correlation map between the precipitation over Eastern Africa and the global SST. Apart from the Northwest Asia, you also have this very strong correlation, significant correlation over the East. So could that be something bigger than the Northwest Asia itself, but like a bigger pattern? And the second question is, there has been a lot of works by the group of Chris Funk on the Western gradient in the Pacific and its link with the March-April-May rainfall. And I don't know if that's something that you could link with what you're showing here, because you talked about the PDO in the Pacific. Is that something that you could link with?
Yes, yes. So for the first one, I think since these are ultimately probably forced by these large SST patterns or globally, so you would see correlation other places too. But that's why we do that idealized simulation where we put SST anomalies at a specific region to test that hypothesis. But yes, I think ultimately if the forcing is really global SST patterns, you would see covariability with other regions too, which might not have directly, which might not be causing the drought or over Africa, but indicating that they are caused by the same forcing. So that correlation in this sense wouldn't imply causality. They could be happening because they were forced by the same SST patterns. For second one, yes, again, people have shown that relationship between global SST patterns and dry conditions over Eastern Africa. What we are again hypothesizing here is that the link need not be direct, need not be just Walker circulation introducing subsidence over that region, but it could be impacting other land regions, which could then introduce forcing over East Africa. So in addition to that direct impact, which we all understand, there could be indirect impacts through land surface feedbacks elsewhere.
Thank you very much. So if there is no more question, I think we can end here. And again, thanks a lot to Michela and Samson for
sorry, Roger, I saw a new question in the question and answer box is from the. Can we check?
Okay, so this is from Roy. He said, in that northwest warming, are the model considering the role of strong volcanoes? Also solar indirect influence in the form of NAO. NAO has influence on the March-April-May East African rainfall.
Can you repeat that question? The last part of the question, what other
so does the model take account the strong role of volcanoes and also the indirect influence of the solar indirect influence in the form of NAO?
We haven't looked at that. I think that's an interesting idea. We could look at if volcanoes have had impact on land surface temperature over that region, then to see if we see a role for them in that variability. I think that's a good idea that we have not really dug into, and which we could. I think that's important. NAO also, that's something we can look into as well. Again, we have not looked at what causes that variability in Northwest Asia temperature in detail yet, but I think these two avenues are potentially good paths forward.
All right. Thanks, everyone. Thanks very much, everyone. And thanks, Michela and Samson. It was really great to have your talks and very great perspective. And I think the webinar ends here if there is no comment from WCRP or the International Monsoon Office.
No, from my
Any
side.
comments from the IMPO, WCRP?
Yeah, good listening to good talks. And people also raised a lot of questions. That's interesting. I think there are some questions which on the chat box, which we may have missed, which can be passed on to you through email or something so that it can be answered. And finally, all the question and answers will be posted on the webinar webpage. And the recordings will be finally launched on the YouTube channel of IATM, as well as earlier it is supplied to from WMO to IATM and IMPO. Within 1 week, we'll put it up.
Thank you, Raja Gopal. And as I said also, if you want to know more about the African Monsoon Working Group, please reach out to us. We are open to collaboration, and some of the research gap that has been identified by the two presenters, we can think about how to address them, whether in the form of proposal or research over the region. So just reach out to us anytime. Thank you so much, Will.
Thanks, everybody.
Thank you.
Thank you. Bye.
Bye.